Hello, everybody, and welcome back to Geography 341, Weather and Society. I am Dr. Zach Hilgendorf, and in this short lecture, we're going to be talking about latitudinal energy variations. So we've kind of alluded to it in past videos. We're going to talk about it a little bit more directly. This is a short video, just kind of highlighting some of the differences. So we've talked before that there are 1.734 times 10 to the 17th watts per meter squared of radiant energy coming into our Earth system. On average, 341 watts per meter squared averaged over the surface. We know that radiant energy out is also equal to 1.734 times 10 to the 17th watts, or 341 watts per meter squared. But there's some differences across our planet here. One of them is that just by definition and by how the rays are coming into our planet, there's more radiant energy in near the equator, between 23.5 degrees north and south latitude. Those are our subsolar points, right? That's where our subsolar point deviates from season to season, which means there's less radiant energy going into the poles. We've seen this from the calculations we've been doing on insolation intensity. That says that radiant energy in exceeds radiant energy out along the equator. But on the flip side of that, radiant energy out exceeds radiant energy in near the poles. That flip point where you have more radiant energy coming in than out versus out than in actually happens at about 35 degrees north and 35 degrees south latitude. When we look at this diagram here, and you can see exactly that. So annual outgoing radiation, if you look at the top, is much greater than net loss, or sorry, than the amount coming in, because that insolation intensity is so much lower. But once you hit about 35 or so degrees north latitude, or sorry, north and south, see right about this point here, that's where you go from having a surplus versus a deficit. So here we've got a net increase or net gain of annual incoming radiation, all the way down to 35.5 degrees south and where it flips again. You can see that line right there. That's our annual incoming radiation. So the average net daily radiation at the top of the atmosphere can be seen here. And this kind of shows some of the nuances a lot more directly. So here we've got average daily net radiation, watts per meter squared. And you see those in those reflected as the colors and, we'll say contour lines throughout our world. So big surpluses around, for example, the Indian Ocean, where you see 88 watts per meter squared daily, or 88.3 in the Pacific Ocean there, 70 to 77.4 in the mid-Atlantic, kind of off the coast of Africa, between Africa and South America. But you see that flip to negative values. You see near the Antarctic, all the way down to the bottom, negative 114 are lost, versus up top we see negative 110 are lost near the Arctic. So we see these are just kind of, it's not perfect. So because of this, or the reason being, is for a few different reasons. We have this, because there are these big differences in intensity near the equator and lack of intensity or deficits near the poles, you're getting this big mixing of energy from A to B, or from the poles to the equator. Where within the equator, and until about 33.5 degrees north and south, you've got warm air, sensible heat advection, which is moist air and latent heat advection. So advection just refers to the transport of something from one region to another. As far as we're concerned, advection occurs anytime an air mass moves. When a warm air mass moves into an area previously occupied by a cooler air mass, warm air advection occurs. So in this case, the equator, air from the equator moving into air towards the poles. Cold air replacing warm air is known as cold air advection. Meteorologists are most interested in the advection of variables like temperature, moisture, and vorticity. And we care about this because this is what sets up these massive global patterns that we care about, is this exchange of warm to cold and cold to warm. So warm air going up from the equators to the poles, you have warm air and moist air advection, sensible heat advection and latent heat advection. Likewise, you've got cold air advection and dry air advection of that cold air coming down and filling in areas within the equator. So what drives the generally expected weather that we call climate? What drives our weather? Well, it's simply put, after all this, it's the uneven distribution of thermal energy in the atmosphere and seasonal changes in the distribution of thermal energy within our atmosphere. Or you can call it solar energy as well. So that's all for this one. Like I said, really quick video. I will see you in the next one. We're almost done talking about energy and heat for the present, but it'll be a continuing thoroughfare for the rest of the course. But I will see you in the next video.